Okay, it looks like it's set up. Um, yeah, just making sure. So just as I was stepping outside, we had a monsoon here. So I was sure I was going to be late, and I am maybe a little, but we're ready. So tonight we're going to pick it up where we left off in chapter 13, which is our introduction to ANOVA, or analysis of variance, which is, at least in our case, going to be used to test hypotheses about the differences between three or more population means. Now, it's a much more complicated setup than what we're used to seeing. There's a lot of calculations involved, and we'll do them by hand maybe once just to get a feel for what they're like. But sooner or later, we're going to lean on our calculators because, that's what they're for. There's no point in making extra work for ourselves, but we would like to still understand what's going on behind the scenes. Okay, hold on. So that's where we're heading tonight. Now, I do want to point out too, I did manage to get those problem sets put together that I mentioned yesterday. So I think we should probably maybe take a pause on the new material and go through the problem sets that I wrote. They're for chapters 9 and 10. And I did that because we have the first midterm, which I'm still working on getting it posted, by the way. And it's going to be based on chapters 9 and 10. And in order to give you as much flexibility as possible, it'll be open right away, like all the other assignments, but it won't be due until the very last day of the class, which I think is August the 7th. So you'll have plenty of time to get it done. But I think that we probably could use a little bit more practice with these concepts. So in a second, I'll show you where they are. And you'll get a look and see what kind of questions they are. And that way we can start to work on them together tomorrow night. Okay, so the first thing we're going to do is go to Blackboard and take a look at these new problems just to see what they're all about. All right, so let me get that open. So we'll start with chapter 9. And they're sitting here right in the top, chapter 9 problem set. And there's a second half to that. Let's get that open. It's called problem set number 2. Okay. So now remember, chapter 9 is where we first started doing hypothesis testing about either a single population mean or a single population proportion. So if I remember correctly, I've got all the means on part 1 and the proportion questions are in part 2. Okay, so if you look at these carefully, you'll see we're trying to test hypotheses about population means um, and how many. Oh, wait, actually, number 5 is a proportion. So, let me see what's on part 2. I don't remember. Yeah, I guess I must have just decided to write more purport. I mean, there's altogether 8 now, so that means there's 4 for means and 4 for proportions. By the time we get through this, we'll be experts. Okay. So the other thing, if you go to chapter 10, I've done the same thing there. And of course, now chapter 10, for the first time, we were looking at 2 different population means or proportions, as well as confidence intervals. So now, by the way, these are not meant to be handed in. These are just for practice purposes. So, don't say, "Oh my God, when do we hand these in?" No, these are just for for you to get some practice with. And if you don't have time to work on them, well, you'll be watching as we go over these tomorrow, and you'll be able to see what the correct answers are. And so for these, we're looking at two means. If you remember, there are more different cases when there are two means. Okay, so we need more problems. And and while we're doing these, I guess another benefit of doing this is that we'll have more opportunities to learn some of the special features of the calculators. I'm not sure if we covered all of them. There's always some more, to learn. The calculator is absolutely amazing what it can do, but you have to know where to look. And so part two is going to be, oh, you know what this is for? This is for the matched pairs. Remember, we went over this where there's a relationship between our two populations. And so we have to treat this a little bit differently than the other cases in chapter 10. All right. Now, with all that being said, we also have something that I call my sample midterm, where everything's all together, mixed together as if it were a regular test. And during the school year, the actual test that you would take in the classroom would look a lot like the one you're going to see here. But since we're doing this online, of course, the format will be a little different. Okay, so here's an example of what I mean. When I give exams in the classroom, I always have a set of what are called fill-ins, which are short answer questions designed to test your knowledge, but that do not require a full problem in order to test test your knowledge. Like, for example, what is a type 1 error? Well, you're at home. You can look this up. So there's not going to be any fill-ins. There's actually a mixture of questions. When you write exams using the MindTap system, there's a limit to what you can do. So they have some problems are fill-ins, not exactly fill-ins, they're more multiple choice. And then some of them you do have to do the calculations yourself. But even then, if I remember correctly, it is a multiple choice. So it's just a little bit different than what you're seeing here. But you still should know all these concepts because you never know when there might be a fill-in in the final exam or the midterm that looks a lot like this. So, and the advantage here too is that everything's jumbled together so that you can't tell what it is just by looking at, the order of the questions, which you probably could do in chapters 9 and 10. All right, so I'm going to save these for tomorrow night since you just found out about these. And I'll post the solutions when we're done so that you can study from them if you want. Um, and so over the weekend, I'm pretty sure that I can get that exam set up. The exam itself is written. It's just a question of setting it up so that it doesn't interfere with your average on the assignments. Because if I don't do it right, it will perceive this test as another assignment and will affect your average. And we don't want that. It's meant to be completely independent of your MindTap assignments. Well, you'll see when we get it up there. All right. So I guess with all that being said, we can now go back to chapter 13. Now, we didn't get very far yesterday, so we can kind of go back to the beginning and remind ourselves what we were actually doing. And so let me get that open. Chapter 13. Oh, and so by the way, in case I didn't mention it, the second midterm would be 11 and 12, and then the final would just be 13 and 14. All right. So it's essentially three two-chapter exams. All right. So in other words, the final is not comprehensive. It just refers directly to chapters 13 and 14. So how much more time do we have here? About 3 weeks, I would say, until all of this is due, which sounds like a lot, but you know how the time can get away from us, during the summer. All right, and anyway, let's get this open. Yes, it gets away from us very fast. Now, I think I mentioned yesterday that this chapter doesn't use the chi-square distribution. Instead, we use the F distribution. And so we'll have to remind ourselves how that works. So if you notice, there's three F tables. Because the F distribution uses two different degrees of freedom, we need, the rows will give us one degree of freedom, the columns another, and there's no room for anything else. So we need an entire table for each possible value of alpha. That's why there's so many F tables. All right, let's get these going. Okay, here we go. All right, I better get my notes ready here. Today's the 15th. Okay. So if you're wondering what I'm doing there, when I'm writing with a tablet, you've got to have these characters are here. They're not printable. You can only see them. There's a button up here that turns them on and off. And these are unprintable characters. And what they do is they advance to the next row. If I don't put these in here, then I'll only be able to do one page, and it would refuse to go on any further. So this is the only way I can think to get around that issue. There's probably something more sophisticated that I could do, but I don't know what it is. So, all right, let's get this saved. All right, it looks like no. All right, give it a second. Now, I do want to point out here that there are actually two parts of this chapter 13. The first one is called Experimental Design and Analysis of Variance. The second part is experimental design and analysis of variance. So I think, if I remember correctly, that we do not cover this part in the curriculum because it's even messier than what we're doing in part A. And honestly, this isn't really the most important application. if you're a business major, this is good for certain things, but not necessarily for finance and economics. So 13B, we probably won't have time to look at it because it's just not worth our while. We're much better off spending our time with regression analysis because that is critically important to all business majors and especially economics. So rather than spending time with this very complicated but not terribly useful application, we're going to focus all of our attention after that on chapter 14, which is regression analysis. And so I'll close this one up, 13B, because we're not going to need it. But this one we definitely do need. All right, here we go. So there, again, there's a lot of definitions we have to get used to in this topic. It's very different than other chapters we've covered. What, what we've been looking at so far is the so-called completely randomized design, which means that, like I showed you yesterday with the farmer growing corn on his land with different fertilizers, the plots are chosen at random to have the different fertilizers to test to see which ones give us the most corn. And so that's what that's all about. The other approaches require us to have a specific organization to, let's say, the fertilizer. If and the reason for that is because we're probably testing more than one thing at once. Like right now, we can just do a test whether the fertilizers give us the same results. For something more complicated, where you want to see if there's an interaction between the fertilizer results and, let's say, the rainfall, that's when you need these more advanced versions. But that's when the complexity gets much, much worse. And to make things even more problematic, when you get past what we're doing here, the calculator can no longer help us. Okay. So for all those reasons, we're going to skip part 13B and allow ourselves more time in chapter 14 because it's much, much more important in my opinion. Okay. So anyway, so a quick reminder of these terms that are not at all familiar to us. So I'd like to repeat the example I started working on yesterday with a farmer who's growing corn in Iowa, let's say, and he decides to plant, let's say, 5 acres each with one of the three fertilizers. So we break this up. Altogether, we'll have 15 squares. So you have to visualize this is the farmer's land. We've got three fertilizers, which will scatter around evenly. And then the rest would be F3. And then you're going to take the results. We're going to go out there and count how much corn was produced in bushels, let's say. And we're going to make up a chart. And the chart would show us how much corn was produced in each of these plots. So here it would be organized into columns. Let me show you with the table. And here it would be organized in such a way the information would be together in one convenient location. And so that we can compare the results side by side. All right. So in other words, you would have, let's say, F1 here, F2, and F3. And then you would just have whatever. Oh, I see that we're missing a row. Okay, hold on. So I'm just going to make up a bunch of numbers. Let's say here we have 10, 9, 11, 12, 9. Over here we have, let's say, 8, 12, 10, 9, and 13. And then over here we could have, for example, 6, 8, 12, 9, and 6 again. And then what you would like to find out is whether or not the means are equal for all three fertilizers. And so the test you would run would be either they're all equal or they're not. Okay. So, like in the previous chapter, we're going to have a right tail only test. Let me make that a little bigger. There you go. That should do it. And then, you can imagine you're going to compare the means to each other, but it's more than just that because, there has to be a formal mechanism for saying, are they all the same or not? Okay. So we'd have, let's say here, mean of each of the three fertilizers output. And then the alternative has to be not all are equal because there's so many different ways they can be different. That's like sort of like it covers all the rest. In other words, anything else besides all equal is included in this alternative hypothesis. And then that's when the fun begins, when all the calculations start kicking in. So a couple of other things we have to keep an eye on. A factor means the variable of interest. Okay. Very difficult. I find this notation, this terminology to be very awkward. Um, I think it's because it's coming from a different discipline than what we're used to. And so the naming conventions are just very strange. So, for example, here, a factor is the variable that we're studying. So, in other words, in our case, the factor would be the fertilizers that we use. So, if it's the factors that we're trying to compare to each other, the fertilizers. So, there's only one factor here. And the treatments, again, the treatments are just these are the three columns. In other words, how did we test this hypothesis? These three columns are known as treatments. How did the corn do with F1, with F2, and F3? Experimental units. Well, I guess you could think of that here as the acres of land on which we grew the crops. And completely randomized design. That's what this is all about. Now, the reason why it's done like this is to control for other factors. In other words, um, given this enormous piece of land, let's say, this could be hundreds of acres. Some parts of it are bound to be drier than others. Some are bound to be wetter. Some are maybe hotter. Some are colder. So by randomly scattering the fertilizers around, we're hoping to more or less eliminate that as a variable. In other words, if we've got F1s in both hot and relatively cool parts of the property, if we have F2s are in different parts where some are wetter than others, you're kind of not allowing that to influence the results. So a randomized design is designed to make sure that we're really only focusing on one thing only, and that is our factor, in this case, the fertilizers. If you're looking for two things, like factor, let's say the fertilizer and the rainfall, then you'd have to organize this a little bit differently. You'd have to make sure, for example, each one of these rows is a different level of rainfall or something like that. And that's how you would set it up. But here we're not doing that. We're just randomly throwing fertilizers into these different acres to see what we get. Well, all right then. So that's the one we're doing here. And by the way, it may seem like a complicated process when we do this, but it's nothing compared to the other two. All right. They really are messy. And that's why the calculator can't handle them. That should tell you something about them when the calculator can't do them. So no matter how many population means we choose, it doesn't just have to be three. It could be anything from three up to any number we want. And if the null is rejected, it means that at least one of them is different. We don't know which one. That requires separate testing, but at least one of them is different from the others. Okay. Now, I did mention last time that we also have several assumptions here. That's always true. I mean, even if we don't explicitly mention it, every one of these tests that we've done has assumptions. Here, the assumptions are fairly strong. Um, Sometimes it's not that hard to match those assumptions. Here, it could be a little tricky because we have to assume three things. And of course, if these are not true, then our results will be less than accurate. And we'll just repeat this one more time. ANOVA number one, the dependent variable, which in this case is the yield of the crops. Okay, so in other words, we're assuming in this setup, y is a function of x means crop yield fertilizer. So what we're assuming is that the yields are normal. So the response, oh, and there's another case where the dependent variable, we all know what that means. But in ANOVA world, they have to have other names for everything. They call that the response variable. Just to drive us crazy, okay? Is normally distributed. Okay. Number two, the variance of the response variable is it's the same, is equal for all the populations in our study. And three, the observations, meaning in this case the crop yields, must be independent of each other. There's no pattern to them, is what we're saying. Okay, now if we can live with all those assumptions, we can carry on. I don't know what's going on. The mouse is misbehaving here. Sorry. You know what it is? If I leave the stylus on the tablet, it causes the mouse to freak out. All right. Um, so yeah, what they're trying to illustrate here is that we have the mean is in the center right there. These are the three sample means. And you can see, they're all reasonably close to the center. They should be good estimates of the population mean. And I think what they're trying to show us is that in this case, it's clear that all the means are drawn from the same probability distribution, and here they're not because the null is false. Here the null is true. All three of these um, are, in other words, we're drawing when the null is true, what we're effectively doing is drawing our samples from the same distribution. If the null is false, it's as if we're drawing them from three different distributions. And that's because you can tell because they're so far apart from each other. All right, so now here's some of the calculations. Now, do not faint when you see the formulas. They look terrifying, but they're really not that bad. Once you get the hang of it, um, they just look awful, but the concepts are not that difficult. We have between treatments, and again, that terminology, it's just so non-intuitive. Within treatments, and then we compare them with the F-test. So now look at this disaster. What is this supposed to mean? Okay, now here's what we have to do. So let me copy this. So I'll tell you what, just so we have that information right in front of us, why don't we go ahead and actually calculate these three means? I think it'll be a lot easier to explain what's going on. What do you have? This is 51 over 5. And we'll call this X1 bar, okay, the mean of the first sample. Okay, and that's going to be 10.2. This one is 52 over 5. It's it's only 41. So this one has the potential, at least, to be different than the other two. It is a bit smaller, as you can see. Now, the notation that they've introduced for the first time, if you got a glimpse of this, you see that right here, it's got two bars over that X. What in the world is that all about? So this X double bar, as it's called, is the average of the averages. What in the world do I mean by that? Well, you're basically adding up all the elements in the entire table and dividing by the size of the table, which, because all three of these are equal sized, we can speed it up just a little bit. So when they all have the same number of elements, which is not always the case, you could do this. If not, then you're just literally adding up everything in the table and dividing by the number of elements. Okay. So if not, then you will add up all the elements in the table and then divide by the number of elements in the table. All right, so for our purposes, we're going to get, so it was 10.1, 10.2. Oh, no, sorry, it was 2 and 4. And the last one was 8.2. All right, let's see what we get. 9.6. Now, this in the world of ANOVA, this sometimes is referred to as the overall mean. Sometimes you hear it called the grand mean. So then let's look at this scary formula. Now, the way it's written, although it's not super obvious, J equals 1 to K means um, it's numbering the columns. So you could rewrite this in our case as, oops, sorry, that's 2. All that would be divided by 3 minus 1. 3 is K. K is the number of columns. Let's write this down. J is an index, but K is the number of columns. So if you plug in these numbers, okay, let me split the screen so I can see what we're doing. So remember, this double X double bar is 9.6. So the first mean is 10.2. Oh, sorry, this is 10.4. I copied it wrong. And then the third one was 8.2. And then all of that. Oh, I'm sorry, I missed the five. Hold on. You know what? This is, let me do it down here so it's a little neater. All right, that's much better. All right, then we just plug it into the calculator and let's see what we get. Okay. So actually, this is 1.4 squared. It's zero point 0.6. 0.8, negative 1.4 squared. All right, so let's see what these are. Um, 1.8, 3.2, 9.8. So at long at long last, we finally have an answer, 7.4. So what does this number mean? Well, it's labeled MSTR, sum, sorry, mean square due to treatments, which means in this case the fertilizers. Now, you're probably wondering, well, what is that supposed to mean? Well, it's part of the test statistic. And there's think of it as a building block approach. We've got these different pieces we have to combine in order to come up with our test statistic. Or if you prefer, you can think of it as the average squared difference between the sample means and the overall mean. So in effect, it's like the variance for single population. Oh, and by the way, because we're using the F distribution, we're going to need to specify two different degrees of freedom. So here, the degrees of freedom is K minus one. Okay. Now, the other thing we need is the mean square error. Oh my God, this just never ends, does it? This stands for mean square error. And this involves the knowledge of the sample variances. So you're going to have for each column or each treatment, Now, NT means total elements in the sample, which in this case is 15. K is the number of columns or factors, sorry, treatments, which means in this case it's 15. Well, all right, I'll write the formula now, but it's going to be 15 minus 3. So once again, we'll plug in the numbers and we'll see what we get. Um, oh, have we already calculated the S squares? Oh, I bet we didn't. All right, I'll tell you what, let's see if they've already done it. We don't want to be here all night. Oh, that's right. These are examples, so I can't look it up. But I'll tell you what, here's a way we can find it out for ourselves. And we can use the lists. Enter into lists. And then we're going to use the command stat calc. There, number one is one var stats. And in that list of output, which we've already seen, you'll find the variances that we need. All right, so why don't we do this? Let's go back up here. And you know what? I'll tell you what, we should have done this in the first place because then we could have done the X bars, but that's okay. We'll come back up here and copy this into our list, which now I think you know how to do this. To get to the lists, you go to stat, enter. Now remember to go to the top and clear out all the old entries. Here's what you have to do. Go to the header, not the top row, but the header with your arrow key and hit the clear button, which you'll find in the upper right-hand corner. All right, so let's do that first. You definitely have stuff in there now. Type in these numbers in the first three lists. Okay, just double checking. All right, so then you hit stat. calc, which is the middle menu, and then one var stats. Oh, you know what? I just realized. I think we can only do this one at a time. Ooh. All right. Well, it's a bit of a nuisance, but we can do it. Yeah, I didn't think about that. Oh, if you start with L1, um, the way you do that is to enter second one, then calculate. The one you want is the third from, no, fourth from the top. Okay. Now that's the standard deviation. We have to square it. Yeah, they had to choose one or the other. So let's you're going to have to go back to the calculator. 1.30384 squared. It's almost exactly 1.7. So this is what we're going to call S1 squared. All right, so I'll tell you what, I'm going to go ahead and do the other two for you. Okay, we don't have all day here. So I guess the only thing we really can do here is write down, it doesn't seem to have any other capabilities here. Write down SX, and then we'll just manually square it. It's almost exactly 4.3. And then for S3, SX, or what we're calling S3, is 2.49, let's say. When we square it, it's almost exactly 6.2. All right. And again, now it's been so long, I forgot what we're supposed to do with them. No, the formula's right here. So we'll just do that right now. So S1 squared is 1.7. Now, by the way, don't square it again. It's easy to make a mistake like that. S2 squared is 4.3. And then the third one is 6.2. Remember, NT is the total, so it's 15 minus 3. All right, so what do we have here? 6.8, 17.2, 24.8. 48.8 over 12 is about 4.067. So this is, remember, we call this the MSE. This sum of squares due to error. And the degrees of freedom in this case is the NT minus K. It's in the denominator. All right, now what are we supposed to do with all this? Well, we're going to create a test statistic based on the F distribution. And so the way it works is this. Once you've got all this done, you can see this little chart is designed to help us figure out what in the world is going on. So you've got SSTR, SSE, SST. This just means the sum of these two. The degrees of freedom are actually the formulas, the denominators of these two formulas. So the F statistic, and we have those two numbers, but I just want to point out that these are the same thing as SSTR over K minus 1, SSE over NT minus K. But we already have them, so we can fill them out as 7.4 over 4.067. And what is that equal to? It's about 1.82, let's say. Now, what do we compare it with? Sorry, no, that's not right. I was thinking of a different example. It's K minus 1 and NT minus K alpha. Now, we've already actually looked these numbers up, if you didn't notice. Just go away. Oh, wait a minute. Oh, that's right. They have their own example. But I just wanted to show you somewhere in here, they're going to mention. Uh, yeah, no, that's fine. But just keep in mind, the tail area is it's always alpha. So just making sure oh, that's right. This is their example. So that means from way back here, remember K was the number of columns, so there's three of them. So we have 2 degrees of freedom here. Now, here's where it gets interesting. In order to look this up in a table, we need an entire table for this alpha. So I've got them, three of them open here that are in Blackboard, but now I don't see them. And I actually did have them open. I don't know what happened. Oh, here they are. So make sure you pick the one that says see, that's the wrong one because it's F.010.10. What we want is F.05. This is it. And it says it in the upper left-hand corner too, right here. The title has it, but also it's right here. Now, here's the most important thing. Do not get confused about this. The way the table is constructed, find not in your calculator, unfortunately. Oh, and one more thing. Don't forget, we were calling this the numerator, degrees of freedom. And here we have the denominator, degrees of freedom. So numerator, degrees of freedom, comes from the top row. Denominator, the freedom, comes from the first column. So let's take a look. 2 and 12. Making sure that you've got the right table in the first place. We have 2 degrees of numerator, degrees of freedom here. 12 denominator, degrees of freedom right here. Oops. So where do they intersect? Right here? Okay, this is the column with 2 numerator degrees of freedom. So that means our critical value is 3.89. Anything to the that is larger than that means we will reject the null. And this is, of course, our rejection region. Test statistic is 1.82. And of course, you can see that we will not reject the null. That all 3 of these are equal. So in spite of the fact, remember from the very beginning, we were concerned about the third column being kind of low. It's not low enough, apparently, to reject the null that they're all equal. Close enough, okay? Well, now you're probably saying to yourself, that was a nightmare. But I have some very, very good news for you. We can do this on the calculator. Now, since you've already put these in your lists, although I'll tell you what, let me go back and show you the chart again in case you didn't get a chance to finish it. We're going to need it right now. So here's the data. I'll give you a minute to make sure that your lists are caught up, and then I'll show you the secret of all secrets, how to do this in your calculator so you never have to deal with this again. Although I don't know if the MindTap assignments will ask you for these individual components, but it doesn't really matter because even if they do, the results will show you in great detail where the numbers came from. So in other words, they won't just give you the test statistic, they'll give you the details how they got there. So I can hear you saying this is the best investment I ever made, this calculator. And it probably is. All right. So with all your lists in place, in order to run this test, what we're going to do is this. So enter the data into lists. Then you're going to hit stat, tests. And if you scroll down far enough, you'll say, whoa, wait a minute. Do I recognize that at the very bottom? Nova. Now, this only works for the technique we're looking at here. It would not work for part 10B. That's another reason why we're not going to go over that. Hit enter. Now, here's where it gets a little bizarre. You're used to having it more or less prompting you for everything. Because the calculator doesn't know how many lists you have, it's going to open up, it's going to look like this. And you're going to look at it and say, well, what am I supposed to do? So you're going to enter the lists by typing L3. And remember, you get these by typing second one, second two, and second three. And once you get to that point, close the parentheses, hit enter, and oh my God. So if you look at those numbers, here's the test statistic. All right, and this is good because it shows that we did this correctly. It has a p-value, which we can't do otherwise. And we'll just note over here that the p-value is greater than alpha, which means that we do not reject the null. Now, the titles here are, again, there's just so many names. Um, so the 7.4 in the book is the MS, not that one, MSTR. Okay. Then the error, well, that one actually is called error. DF equals 12. SS is 48.8. And then there's another entry here. MS is 4.067. That should look familiar. And if you scroll back, you'll realize that that's what we got for the second one, which is called MSE. And there's also a standard deviation listed there. We don't really need it right now. This is for the more advanced versions of ANOVA. So we're good. Now, if you want to use the test statistic critical value approach, you still have to look that up in the table. This F212.05, that you would have to look it up. The other alternative is simply to use the p-value. Then you don't have to look up anything. Oh, so I think you'll agree the calculator is going to save us an enormous amount of time. Now, with all that being said, we can now look at their next example. This is the one that I made up. It's a nice example, but I think we could use more practice. But now we're going to allow ourselves to use the calculator, okay? There's no need to go through this ordeal again. Later on, when we do this in Excel, you'll see that it has these built into the data analysis tool pack. I mean, when you look at this, God, all of that, all those steps. Okay. All right, here we go. What example do they have for us? Chemitech developed a new filtration system for municipal water supplies. There are different methods that could be used to assemble the system. It is narrowed down to 3 methods and wants to determine which one we're going to use. ABC. So the factor is the method by which we are assembling the system. The treatments are the 3 methods. The experimental units are the employees because they're doing the work, and the response is the number of units that we produce. So here's the table, and here's the hypothesis. So guess what we're going to do right now? We're going to enter these into our lists, okay? Not the totals, not the summary, we're just going to do the actual observations. All right, let's do that. I'll give you a few minutes to set up your lists. Don't forget to erase the old numbers. All right, so enter those into your lists. We'll give you a minute to catch up, and then we'll do the ANOVA, and we'll see what we get compared to their results. So we were once again, mind you how to do these ANOVA routine. Stat tests ANOVA. Enter, of course. And now remember, this is the one where it is not really explaining very well what you're supposed to do. And so remember to enter a list in this calculator, you put second and then the number. And so let's try that. Oh, and by the way, don't forget about the commas. Now, it's going to give you a whole slew of details. The ones we really want. Really are these two, but I think we should at least compare the rest with what they're giving us. So the first one, just a little reminder, this is K minus one. In this case, K is three because we have three columns of data. SS 520. And just as a quick reminder, where did they get this from? And also don't forget, this is what this book is calling MSTR. Or oh, I forgot I left out the label. So we have DF equals 12, which, if you remember, is NT minus a K. And then we have SS is 340 and MS, and that's the result of taking the SS over the degrees of freedom. And so let's confirm that. 28.33. Okay. And this is what the book is calling MSE. Now the test statistic is the ratio of these two numbers. In other words, 260 over 2833. So approximately 9.18. And of course, they were giving us a p-value, so we know what this means. P is 0.0038. I didn't notice what the alpha was in this case. And they're showing you all the gruesome details here. It looks like we chose 0.05. And then we accept the alternative that they're not all equal. In other words, the three procedures are not equally efficient at producing whatever it is they're doing there. Okay. And also, if you notice, the degrees of freedom are just happen to be the same as the ones that we were looking at earlier. So if you wanted to look up the critical value, we already know what it is. Um, oh, that's right. We've already seen this one. But our test statistic is, of course, well within the rejection region. And that would be another reason why we should reject the null. We reject the null hypothesis that all three means are equal in favor of the alternative that they're not all equal. Oh, that's better. Okay. So whether you use the test statistic critical value approach or the p-value, either way, you're rejecting the null, which means the means are not all equal. And again, if you notice, we got the same numbers they did. MSTR is 260, MSE is 2833. Okay. Now, the reason why they keep harping on this table is because when we do this in Excel, you'll see that they also produce this exact same table. So we can follow what's going on. So they do these sums of squares. These are coming from formulas. K minus 1, nt minus k. And here, this is the sum of the two, which is nt minus 1. And then the mean square is the ratio of these two numbers. MSTR, the book calls this MSTR, is SSTR over K minus 1. And this one, and then the ratio of these two is our F statistic, okay, or test statistic. And then this one is the p-value. This, of course, means you're looking at the probability distribution for F. And that would be your p-value. Very, very small. Oh, look at this. They're going to do Excel right away. Okay, so now Leave this here for a minute so you can look at it. But they're going to introduce Excel to us very quickly. And again, it's because once we reach a certain point of complexity, it really it doesn't make as much sense as it used to do these formulas by hand or with a calculator. You're going to need to lean on Excel, and eventually, even Excel will no longer be adequate, at least if you go on to more advanced statistics. And you'll need specialized packages whose only purpose is to create statistical results. If I'm not mistaken, the school has SPSS on the ones, at least in the computer labs. And that's a fairly well-known package for the social sciences in particular. And the advantage of that is that a lot of the inputs, you don't really end up typing results or typing formulas or copying results or anything. It's basically menu driven. But of course, we're assuming that the data is on a disk or, flash drive or whatever. So you don't have to type anything. But instead of typing commands or something like that, you're being asked to do, menus. And that does make things a lot simpler. Now, there are some packages that do allow you to create your own equations. Uh, but, why would you do that if it's not necessary? The other thing that's changing right now is that AI is getting itself involved in everything, including computer programming. So if you're using a package that requires like code, it can probably help you with that. But this is all down the road. Like, imagine yourself finding a job where you're spending the whole day working with statistics. Well, you have all this wonderful background, but there's going to come a day when it's going to start getting more advanced, and you have to have the latest tools available to you. So the more you learn about these packages, the better. Okay. Also, I don't know if you may end up taking classes where you have to create projects based on real data. If so, you can certainly use Excel or something more powerful to get your results. It's understood that you're not going to do this all by hand with a calculator. All right, anyway, with all that being said, how do we do this in Excel? Let's see. I'm not positive that this is in my Blackboard folder. Let us check. Oh, you know what I forgot to do here? You see how it says hidden from students? When I put files in here, I have to remember to click on the button that's not visible to students to visible. And sometimes I do forget. So I have to keep my eyes open. That's interesting. That's the only one that I see. What do you know? That's the right one. So let's get this thing open. Worked out well. So what exactly are we supposed to do? Now, this is the one we just did a few minutes ago. This is the Chematech setup. So you've got to make sure the data is organized correctly, of course. So we'll go to Excel, and now they're telling us to choose a Novus single factor. That's what this section is based on. The other ANOVAs you see listed there are coming from section 313B, which we're not going to do. Like I said, so we can spend more time with regression analysis. So why don't we come in here? So all the ANOVAs are on top. Now, what we just did is called a single factor because the only factor here is the method. Or like the corn example I gave you, the factor, that was also one factor. The factor was the fertilizer. The two factors are for cases where we're comparing two things at once, like fertilizer and rainfall or something like that. So we're not going to use those here. Now, here, this is a matrix. We're going to choose all of them at once, include the headers, but make sure you click on labels in first row. Alpha is 0.05, but you can change that if you need to. And then the output range, we'll leave it right on here. We'll choose, click on output range E1. That's where it will start. Right. So let's see how it did. Wow. So those numbers should look familiar. In fact, it's even got some more new numbers that we didn't have. These are just summary statistics for the three treatments. Then here we have, now again, you see, this is so, it just is insanity. There's always some new name for this. This is what we were calling, all right, over here, these S's were what we were calling SSTR. And SSE. Now, if you look in the calculator, remember when we ran that ANOVA test a few minutes ago, it gave us an enormous output. Look carefully at it. This is what it's calling factor. And the one below, the fact calculator is calling it error. Just have to get used to this stuff. Okay. And then, of course, we know how these were calculated. And now MS is the ratio. This 260 is the ratio of these two numbers. The 2833 is the ratio of these two numbers. The F statistic is the ratio of these two numbers. And then finally, we have the p-value. Now, here's an added bonus. Look what Excel did for us. You don't see this every day. F crit, that's our critical value. If we want to use it, it's right there. We don't have to look up anything. Oh, wow. And look how fast it is. How much work do we have to do? None. All we have to do is interpret it. Okay. I mean, it must have taken half an hour to do this by hand with my original example. This was like 30 seconds. So yes, it's here if you want to use it. You can use the calculator, you can use the Excel. Just be careful that you enter the data correctly and you're all set. And also know, how the hypothesis works, hypotheses work. You're the one who's still responsible for understanding this. Now, this one involves three cities. Is there a difference between the difference in the mean examination score of the employees at the three plants, NCP manufactures printers and fax machines at plants located in Atlanta, Dallas, and Seattle. To measure how much employees at each plant know about quality management, a random sample of 6 employees was selected from each plant, and they were given quality awareness examinations. So the factor is they were trying to compare is quality awareness, the treatments of the three cities, the experimental units of the employees, and the response units. or the exam scores. So we're going to go through the same routine as before. We're going to have the null that all three means are equal, the alternative that they're not. We have to give it a level of significance. And of course, you can go through and do these all by hand. Don't have to. We know why, because you can use either Excel or your calculator. Okay, so here's my challenge to you. Imagine that, like this is an exam of some kind. So what we need to do is run this test and make a decision about whether or not the means are equal or not. You can put together a little table like this if you want to, because it's already in the printout. But what I'm going to do is say, all right, and this is what I would do if we were in a physical classroom. Say, all right, I'm going to give you a few minutes and you're going to work on this and come up with some results. Okay. So first you put these in your lists and then you run the ANOVA routine and then you're going to make sense out of it. Given that these are the null and the alternative hypotheses, you can let alpha be 0.05 and then it'll give you everything you need to know to run this test. All right, so why don't you go ahead and try that? I'll give you a few minutes and then we'll see how you did. So of course, don't forget to erase the old data. And you know what? For the first time, we have a different number of values. Interesting. Oh, you know what? The only problem is, all right, when we're done, I'll go look up the critical value if you want it, because you need the F tables in. I mean, you do technically have them there. Um, yes, they're using 0.05. So you can find these in Blackboard. Just be aware, remember the top row is the numerator degrees of freedom, and the first column is the denominator. Don't get them backwards. You'll absolutely get the wrong answers if you do. So, all right, let me put it back. So you can see the data. There we go. Now, of course, once you've typed all your information into the lists, making sure that you've done it correctly, this is the NCP example. After entering the data into the lists, I'm going to do edit, or sorry, stat tests, letter H, ANOVA. You know, I just thought of something. This Chematech one, yeah, I'd like to collect this one. I think I forgot to mention that. Why don't you, if you already finished this one, why don't you save it and send it over here? I just realized I never quite mentioned that part. Yeah, this is the Excel. This was meant to be the Excel assignment for this chapter. So even though it didn't take very long, why don't you save that and send it over here in case if you haven't already, okay? Just to make sure there's no misunderstandings. Anyway, so let's go back here, ANOVA, enter. And then, of course, remember, this is the unusual one. It sits there waiting for you, and then you have to say, oh, what does it want? Oh, that's right. Remember to enter these. You have second one, second two, second three, all separated by commas. Yeah, don't forget the commas. And okay, so that leaves it comes back one way ANOVA. So I have, and then it's got factor. Remember, this is SSTR. Oh, hold on. Then error, degrees of freedom is 15. Oh, and don't forget SS is 430. And then finally MS. And this is what we called earlier MSE. The test statistic, that should be 258 over 28.667. It's almost exactly 9. Now, I just realized, did I write down the p-value? Yes, there it is. Good. All right. So if we wanted to look up the critical value, so it was 2, but now keep in mind there are 18 observations this time. Now, the only thing is, I'm not positive this table has enough rows for this. That's something we've got to really watch out for. Oh, thank God it does. All right, here. So in other words, it's the intersection of 2 with 15 was pushes right here at 3.68. So our critical values here. But that test statistic, that's pretty large for the F distribution. So you can see that, of course, the test statistic is in the rejection region. So the null hypothesis that all three means are equal is rejected in favor of the alternative that not all three are equal. Okay, and make that bigger so you can read it. Now the p-value will tell us the same thing, of course. Alpha was 0.05. So we reject the null, that the three means are equal, and accept the alternative that they're not all equal. Okay. And that just means now, based on this problem, they had the three cities. May have had a typo in it, but anyway, reject the null. Whether we use the p-value or the test statistic. All right, so I think we're getting pretty good at that part of it. Now, you're probably wondering, well, imagine that we have a large number of means to compare to each other. And, we're trying to find out, really if one of these different cities in which we're building our product is more productive than the others. The ANOVA by itself can only do one thing, and that's say, are they all the same or not? It's a starting point, but it may not be enough. It's possible that we need to identify which one of these cities is different from the others. So how do we tell which of the um, treatments is different from the rest? That properly, we need another test. Of course we do. What else would we be doing here? Now, this is given to us by a very, very famous statistician named Ronald Fisher. Okay, now keep in mind, remember, he's the one who invented the F distribution. So, this guy knows what he's talking about. Okay. So, he was one of the early, he would have been alive during the early 20th. And a lot of the things that we use in statistics, even it may not be super obvious, but they were invented by him. Oh, there it is. I forgot. I left out the important detail. They still figured out what I meant. Um, he lived from 1890 to 1962. It says here he was a mathematician, geneticist, and evolutionary biologist, known as the father of statistics. Yeah. Oh my God. So that was his idea. The null hypothesis, randomized experiments, ANOVA. Oh boy. So he's a heavyweight, all right. But anyway, what test did he come up with? Now, here's the funny, this is everyone has a chuckle over this one. Least significant difference. What is the acronym for that? LSD. So, everyone says, "Oh my God, look at that. It says LSD in the page." But what he was talking about least significant difference. So, here's how this thing works. So, you notice the subscripts, I and J, meaning we compare the means two at a time, and we'll have to compare all of them. So let's start writing this down. Here's what LSD looks like. Actually, this is supposed to be an I. And you notice these are always going to be two-tailed tests. You just want to know, are the means equal or not? Then, now look at this test statistic. Oh, we need that MSE in there. Okay, now that looks very strange. Now, here's where it gets even more bizarre. The way we carry out this test is maybe not what you're expecting. Um, what we're going to do is create this LSD statistic. Now, by the way, I don't believe there's any way we can do this in Excel or on the calculator. This one we have to do ourselves. And so we reject the null if the absolute value of their differences is greater than the LSD. Otherwise, do not. So that means we don't know any of them, any of these pairs could be significantly different. We don't know which ones they are without running a test like this. Let's see, do they have one here? Oh, here's Chematech again. Let's go revisit Chematech. Because we do need the data. Which one is Chematech? Let me make sure I remember which one is Chem. Okay, here we go. Oh, yes, ABC. All right, that's Chematech. So I'm going to see if I can copy the data here. No, this is my example. No, that can't be it. It must be this one. You're right, because F is 9.18. So this is, oh, but you know what? Oh, there they are. There's the results. So we need, okay. What we're after is MSE. All right. That's what we're really after. And that would be right here. That's the 28.3333. All right. Then the others are easy because they're just the means. Oh, okay. So you know what we forgot to do? We have to look up this T or critical value, and we're going to assume alpha is 0.05. Um, and so we can look this one up in the calculator. And so, you know, it's going to ask for the left tail area. So it's 0.95. Degrees of freedom is 12. So we can look that up. 78 I have. No, they got something. Oh, you know what? It was alpha over 2. I didn't notice that. All right. Sorry, it's alpha over 2, which means we have to fix this. So this is now 975. And let's try that again on the calculator. Yeah, 2.178. That's much better. So what else do we need to know? So it's T alpha over 2, square root MSE. Okay. So that means it'll be uh, MSE is the 2833. Now, all of these have the same number of observations. With Chemitech, I believe it was 5. Yes. All right. That does make things a little bit easier to me. I have 7.33. Oh, okay, that's fine. So now what we have to do is, um, if you go back and look at the data, we had the three methods in Chemitech. Let's go. Here we are. The means were 62, 66, and 52. So basically, to compare them to each other, you're going to compare the absolute values of the differences to that LSD factor. So to compare A with B, for example, that one's less than the LSD. So that means the means are equal. Then we'll compare A with C. That's 62 and 52. That one's greater than LSD, so um, the means are different. And of course, we need B and C. Just, that gives us 66 versus 52 means that, again, the means are different. So the only ones that are the same are A and B. Yeah, so this there I don't think this is that important. I don't believe there's any questions about this in my tab. Certainly not on the exam, but yeah, you can create separate type one calculations for each pair of means that you're comparing. I don't think this is important enough for us to worry about. So that's that. Now, oh, that's right. We already did this spreadsheet. Well, then here's what I think we should do. Um, Tomorrow, we're going to go over all those problem sets from 9, 10, and the sample midterm to make sure we're ready for the midterm. I don't think it makes sense to go any further here. I mean, I did say that the second half of chapter 13 is such a nightmare that we're not going to do it. That way we are freed up to spend more time with chapter 14, which is much more important. So we're going to call it here. So 13A is done. And by the way, if you want to see some formulas, take a look at 13B and you'll realize why we're going to have to skip this one. It should tell you something when it's not even in the calculator. Okay, so I guess that's probably enough for now. So, like I said, we'll do the reviewing tomorrow. What's coming up after this is chapter 14, which is our first look at regression analysis, which couldn't possibly be more important for business majors, especially economics majors. It's their lifeblood. Economists couldn't get anything done without regression analysis. And, we're going to cover it, but we're just going to give you the most important introductory material. You could spend an entire lifetime studying regression analysis. So, but we're going to do the most important basics so you can at least run a regression and get some results and draw some conclusions from it. But we're just covering the tip of the iceberg, to say the least. So anyway, so I guess we'll stop here. Hopefully it stopped pouring out there. And then I'll see you tomorrow. Okay. All right. So good night, everyone.
Thank you.
Thank
All
you.
right. Bye.
Thank you.
I'd see you tomorrow.
Professor, I had a quick question.
Yes.
What, so what should I do about the data analysis Excel sheets?
You know what? I don't think there's any real prospects of us getting that fixed during the course. So I think if you send me an email and remind me about this, I'll just make sure that they don't count for you.
Okay. Okay. Thank you. Bye bye. Have a good day.
All right, bye.